So today we are going to discuss a very important problem involving image processing, electromagnetics and so on. After all, an image is just an electromagnetic field. The image or any object that we watch with our eyes, it is all just electromagnetic fields coming from the object and making an image on the going through the eye lens and making an image on the retinal screen. So we will today ask the following problem. You are given an electromagnetic field F mu nu, or equivalently the 4 vector potential A mu in space time coming from an image, and this field gets rotated or translated. So you are applying a group acts on the manifold. The manifold is, let us say, R3 or R4, either space time or space. Let us say it is space to start with. So G acts on the manifold M. It acts on the manifold M. That means you have an action G cross M to M. Any element of the group G is denoted by small g. Any element of the manifold, which is R3 in our case, 3-dimensional Euclidean space, it is denoted by x, and this goes to G dot x. So if G is a rotation, for example, if G is a rotation, then the group is SO3, the group of all 3 cross 3 real matrices having determinant 1 which are orthogonal. So G is SO3, this consists of all SO3 is the group of all G such that G transpose G is equal to I and determinant of G is 1, and G of course is a 3 cross 3 matrix R 3 cross 3. So such a rotation can be described in terms of 3 Euler angles. First, rotation around the z axis by an angle psi, then rotation around the x axis by an angle theta, and rotation around the z axis by an angle phi. These are called the Euler angle parametrization of the rotation group. Now you apply a rotation to this image field and you want to determine, you do not know what rotation you have applied, you just know that you have applied a transformation, a group transformation, an element from a transformation group to the image field, and then it gets corrupted by noise. So you have an image field, the measured image field can be denoted as F mu nu x tilde, which is nothing but the rotated version of the original electromagnetic field plus a noise term W mu nu x, and you want to determine the rotation because you want to decode from the original image what was the rotation that was applied to the noiseless image or noiseless unperturbed image, what was the rotation element applied to get the given observation. So in general group theoretic terms we have a manifold M, say the manifold is R3, and you can and you have an image defined on R3 or an object function on R3, if R3 to R or C, let us say it is R, and you apply a transformation group, that means you rotate it by an amount, you rotate it by the group transformation G, this becomes a rotated image. Basically if you call this as FGX, what this says is that if you take the rotated image, suppose this is the coordinate system, and suppose you are rotating the coordinate system, you can consider the rotation as being applied to the coordinate system with the object being static, then whatever the new image you get, the new image at the rotated point. So say you have got a Cartesian axis and you have got an object, you rotate it. So you want to know what is the intensity at any point x. So if Fg is a rotated image, its value at Gx will be the same as the original image value at x, which is same as saying that Fg of x is nothing but f of G inverse x. On the other hand, if you rotate the coordinate system by an amount G, then what happens? It is equivalent to applying an inverse rotation to the rotation by G inverse to the original object. So you did G instead of f of G inverse x, you will get f of Gx. So in effect you have an equation like this, you have two images, one is a rotated and noise corrupted image of the original version of the original one. So this can be written as f of G inverse x plus Wx, where W is noise, and you want to estimate the value of G. So the most convenient way to do it is to pick a point x0 in the manifold M and assume that G acts transitively on M. In the case of the rotation group, the rotations act transitively only on a unit sphere or on a sphere of a given radius. So in other words, if x is R3, I will replace x by, I will consider only those x's which fall on a sphere of a fixed radius. So it can be written as some R0 times x cap, where R0 is the radius of the sphere and x cap is a unit vector it's a unit vector, that is x cap belongs to the surface of the unit sphere. So you can write it in this way, and you can write your F2 of R0 x cap as F1 of R0 G inverse x cap plus W of R0 x cap. That means I am confining my attention to the surface of a sphere of radius R0, and from this I can delete I can absorb R0 into the definition of the image. So I can remove this R0 from this and consider everything to be taking place on a sphere of radius R0, or equivalently on a sphere of unit radius by absorbing R0 into this, and I have such an equation. From this I have to estimate the value of G. So I can write, instead I used a notation x in place of x cap for brevity, for simplifying our notations. So F2 of x cap, so F2 of x is simply F1 of G inverse x plus Wx, and I want to estimate G from this. So directly if you want to estimate, say suppose W is a wide Gaussian noise field, then the maximum likelihood estimator of G will be equal to argmax of G cap of minus 1 by n0 integral F2x minus F1 of G inverse x mod square dx, where dx is the invariant measure on the manifold, that is, it is a measure which is left invariant by the group action on the manifold M, or equivalently you can say that G cap, if it is a Gaussian, you are assuming W0 is a wide Gaussian field. In this case this is a wide Gaussian field, that is why you get this. If it is a colored Gaussian field, then this will be replaced by a quadratic form. So in the case of a white Gaussian field, the best estimate of the group element G is given by simply F2x minus F1 of G inverse x mod square dx, and arg min of this, arg min of G over all G. Now performing this minimization is very difficult, because G occurs within the argument of this function. So each time you change your function, you have to do a minimization in a different way. So a simpler way which has been suggested by many people like Reiner Lenz and even my dad K.R. Parthasarathi, who introduced me to this subject and helped me understand many notions in group representation theory and how they can be applied to practical image processing problems. Of course I owe a lot to him. I shall just describe the method based on the theory of group representations. Also called group theoretic Fourier transform. Group theoretic Fourier transforms. How to estimate the value of G? So you have an image model of the form F2 of x is equal to F1 of G inverse x plus Wx, and since you are taking x to be a point on the sphere of fixed radius, the group SO3 acts transitively on this surface. So I can assume that G acts transitively on, that is, this is a transitive action G cross M to M, which takes G comma x to G dot x. Transitive means that if you are given, what do you mean by saying that the action is transitive? Given any two elements x2 and x1 in M, there exists, for every x2 and x1 contained in M, there exists a G contained in G. Here the group is SO3, such that x2 is equal to Gx1. That means it covers everything. The rotations act transitively on the sphere of radius R0, so you can reach any point from any other point by a rotation. But if you have two spheres of different radii, then you cannot reach a point on the outer sphere from the inner sphere by a rotation. Neither can you reach a point on the inner sphere from the outer sphere by a rotation. That is why we restrict ourselves to a sphere of a given radius. Now you simply choose a point x0 on this sphere. Here I am considering the manifold to be S2 itself. Choose a point x0 on the unit sphere and define and fix it, and consider, say f0. Let us say I define f tilde of x, f tilde of g to be equal to f of gx0 as g varies over g. So, I am given the original image is a function on the unit sphere. From that I am constructing an image function, a function on the group by this idea. I take a point x0 on the sphere, unit sphere, operate on it by an element g and define it in this way. So, the same equation, namely the equation which I had f2 of x is f1 of g inverse x plus wx, can also be written as, if I replace x by gx0, this equation can be written as f2 of gx, say let us call this as g1, f2 of g1 x0, f2 of g1 x0 can be written as f1 of f1 of g inverse g1 x0 plus w of g1 x0, as g1 varies over the group, or equivalently f2 tilde of g is equal to f1 tilde of g inverse g1, f2 of g1 is f1 tilde of g inverse g1 plus w tilde of g1. So, an equation on the sphere has been replaced by an equation on the group. Now, I can apply the theory of group theory, Peter Weil's theory of group theoretic Fourier transform on the rotation group. What it says is the following. The Peter Weil theory says the following. Peter Weil theory. So, you are given a compact group, in this case it is SO3. I am going to specialize the Peter Weil theory to SO3. Then I take a representation. I take what is meant by a representation of a group. A representation of a group is a mapping from the group G to transformations on a vector space LV, such that any element G here goes to pi of G, a matrix. Say V is a finite dimensional vector space, then LV is a set of all linear transformations on this finite dimensional vector space, and pi should satisfy the group homomorphism property. That means pi of G1 G2 should be pi of G1 pi of G2, right, and then of course this will imply that, and they are all non-singular, so it will imply that pi of the identity is simply identity matrix, pi of the identity element of the group is simply the identity matrix. So, Peter Weil theory says the following. If you take first you note the following situation, first you note the following thing. If G is a compact group, for example SO3, then I can always choose, and pi is a representation of G, say pi maps G to LV, where V is an inner product space like this, it has got an inner product. Then I can always choose, modify this inner product such that pi becomes a unitary representation. How do you do so? Simply I define a new inner product of between two vectors in V, x comma y 1 is equal to integral pi g x comma pi g y dg, where dg is the Haar measure on the compact group. Haar measure is a unique left and right invariant measure on the group. In fact, on a compact group every left invariant measure is also a right invariant measure, and up to a constant scalar multiple of, up to a positive scalar multiple, the Haar measure is unique. So, it is a shift invariant measure. That means that if you take, as formally if mu is the Haar measure, then mu of GE is equal to mu of E for all G belonging to G, and E is an element of the Borel subgroup, sorry E is an element of the Borel sigma field on the group, on the Lie group G. That is same as saying that if you take any function f and you try to integrate with respect to the Haar measure on the group, now this will be the same as if you shift the function f of hg into d mu g, you integrate it on the group, you will get the same value as the original integral. It is just like the length measure, just as the length or Lebesgue measure is invariant on the real line. Okay, so likewise on a compact group, on any group you can ask, when is this integral invariant under left shifts? Of course, in the case of a compact group, you can prove that left invariant measure is also right invariant, but it is not true for a locally compact group in general. But in the case of a real line, the group is an abelian group and everything boils down to just saying that the Lebesgue measure is an invariant. F plus y dy over the real line is same as f of y dy over the real line. In the case of the Lebesgue measure is invariant under shifts. So this is the group theoretic generalization of the Lebesgue integral. The Haar measure, the Haar integral is the group theoretic generalization of the Lebesgue integral. So you define it in this way, then this inner product, this new inner product, of course this integral will be defined because G is a compact group. So it will, this quantity is a bounded quantity, and so it will be bounded because as G varies over the group, pi G will vary over a compact set. A continuous image of a compact set is a compact set. So since pi G is continuous, you are also assuming that the representation has a continuity property. This quantity remains bounded, and if you integrate a bounded quantity on a compact set, you will get a finite number. If it is a non-compact group, locally compact group, in general this integral won't be defined. So you can define an invariant inner product only for, in general, only for a compact group, for a representation of a compact group. So if you define this new inner product in this way, then you can see that pi h x comma pi h y 1 is equal to integral over G pi G then pi h x comma pi G pi h y dg. I am writing dg for the Haar measure. So this is same as integral over G by the representation or homomorphism property. This is pi g h x comma pi g h x dg, and since the Haar integral is right invariant, this is the same as integral pi g. I can replace gh by some other g prime, which is same as saying I make a transformation of variables to gh is equal to g prime, or equivalently g is equal to g prime h inverse. So it is invariant under right shifts. So pi g x comma pi g y dg over the group G, which is nothing but x comma y 1. That means this inner product is invariant under this under shifts by the group representation. So this is invariant, and this inner product x comma y 1 is invariant under the group transformation, under the group action defined by the representation, group action on the vector space defined by the transformation pi h, which is same as saying that pi h is unitary. That means pi h star pi h is the identity with respect to this inner product for all h belonging to G with respect to the new inner product. So you can assume that any representation of a compact group is unitary, and the Peter-Weyl theory says that any unitary representation can be decomposed. Okay, first we look at a general, which has nothing to do with the Peter-Weyl theory. If you take any if G is any representation and pi is any, if G is any group and pi is any representation of the group in a vector space, then what does it mean? It means that pi G acts on this vector space in a linear way. Okay, and you can consider, suppose W is an invariant subspace of V. That means W is a subspace of V and pi G W is contained in W for all G belonging to G. That is, W is invariant under pi G. That means pi G sends any vector in W to another vector in W itself for all G belonging to G. If it is an invariant subspace, then you can choose a basis for W and extend it to a basis for B by taking W dash, say B tilde, B1, and this is a basis for the entire vector space V. Now relative to this basis, what will be the form of the matrix pi G in the what will be the matrix of pi in the basis pi G in the basis B, BV. So if I write this down, since W is invariant under pi G, this will have the form, say pi 1, it will have pi 1 G, here you will have 0, here you will have something, here you will have something, it will be of this form, right. So by using the fact that W is invariant under pi G, you can see that the matrix of pi G, or equivalent by abuse of notation, you can say pi G itself can be written as pi 1 G 0 something something which may be non-zero. But you see one thing, if W is an invariant subspace, then W perpendicular is also a pi invariant subspace because pi is unitary with respect to the new inner product. You are choosing an inner product relative to which pi G is unitary. right. You have chosen an inner product relative to which pi g is a unitary matrix. So if W is invariant, that means pi g W is contained in W for every g belonging to G, then it implies that pi g W perpendicular is also contained in W perpendicular for every g belonging to G, because pi g is a unitary is a unitary representation. Why is that so? Choose any x contained in W perpendicular. Then what do you have to show? You have to show that pi gx is also in W perpendicular. So let y belong to W. You have to show that this is equal to 0. But what is this? This is nothing but by the unitary property. It is pi g star y, which is equal to x comma pi g inverse y. Because for a unitary representation, pi g star is pi g inverse, and pi g inverse will be pi of g inverse by the homomorphism property. You see, if you look at the homomorphism property, what does it imply? It implies that pi g into pi g inverse is pi g inverse, which is pi of E, which is the identity, which is same as saying that pi g inverse is equal to pi g whole inverse, right. But you see that x comma pi g inverse y, pi g x comma y is x comma pi g inverse y, but y belongs to W. So and W is invariant under G, so and G inverse also belongs to G. So this quantity is again an element in W. So this is of the form x comma z, where z belongs to W, but you are assuming that x belongs to W perpendicular, so this must be 0. So what we have proved effectively is that if W is pi invariant, that means pi g W is contained in W for all g belong to G, then it implies that pi g acting on W perpendicular also belongs to W perpendicular for every g belonging to G. That means W perpendicular is also pi invariant. So in other words, if I choose invariant subspace for V, then I can write V as W direct sum W perpendicular. And you see that I choose a basis BW, an orthonormal basis BW for W, and an orthonormal basis BW perpendicular for W perpendicular. Then this will be a basis, an orthonormal basis for V, and relative to this basis, pi g will have the following form. It will have the following form. Since W perpendicular is also invariant and W is of course invariant, it will be of the form pi 1 G 0 0 pi 2 G. That means it will be reduced. The representation pi g gets reduced to this, where pi 1 G is nothing but pi g restricted to W in the basis BW, and pi 2 G is pi g restricted to W perpendicular in the basis BW perpendicular. And each of this will be a representation of G. This will also pi 1 will be a representation of G in the vector space W, whereas pi 2 will be a representation of G in the basis W perpendicular. Like that I can go on reducing. If W has a further invariant subspace, which is again contained within W, then you can decompose pi 1 again into a diagonal blocks. So into a diagonal block. In this way you go on doing it. So you can write any representation as a direct sum of irreducible representations. You go on decomposing the representation into smaller and smaller parts until you end up at a point when you cannot decompose further. Okay, we are assuming that it is a finite dimensional vector space here. That is, the representation is a representation in a finite dimensional vector space. Then you can write it as a direct sum of irreducibles. Pi j g j equals 1 to m, where pi j's are all irreducible representations. So it is enough to consider irreducible representations alone while doing our analysis for every j. It is enough to consider irreducible representations of the group while doing our analysis. Now you see the following. You take the left regular representation. What is the left regular representation? Lg acts on F at H to give Fg inverse H, where G and H belong to the group G, and F belongs to L2G with respect to the Haar measure. That means it is the set of all functions such that mod F square dg over G is finite, measurable square integrable functions on the group. So this is the left regular representation. You can decompose this also into irreducibles. Although we developed our theory of reduction for only finite dimensional vector spaces, it is valid even in infinite dimensional vector spaces. So G is a compact group. Peter-Weyl theory says that if you look at the set of all inequivalent irreducible representations of the group, they form their matrix elements form an orthogonal basis for L2G. You can prove it very easily using the Schur lemmas, which say that if you take any two irreducible representation pi 1 and pi 2G, then pi 1G, and suppose you take an intertwining operator, that means pi 1G T is equal to T pi 2G for every G belonging to G. So T is an intertwining operator. If pi 1, then this, if of course this implies that if pi 1 and pi 2 are inequivalent, that means you cannot write pi 2G, you cannot write it as S pi 1G S inverse for some non-singular matrix, and pi 1 and pi 2 are both irreducible, then this will imply that T is a scalar multiple, T will be 0. On the other hand, if pi G is an irreducible representation, then and T intertwines pi with itself, then it will imply that T is a scalar multiple of the identity. Okay, how do we prove this Schur lemma? Is very simple. Just take two inequivalent irreducible representations, say pi 1G is equal to T pi 2G. Say pi 1G acts in the vector space V1 and pi 2G acts in the vector space V2 to V2. Then you look at the range of T. So range of T is a set of all Tx as x varies over V1. V1. T is a mapping from V1 to V2, a linear mapping from V1 to V2. So what this equation says is that if you take pi 1G acting on Tx, then this is T times pi 2G acting on x. This is contained in range of T. So it says that pi 1G acting on range of T is contained in range of T. That means pi 1G leaves range of T invariant for all G belonging to G. But since pi 1 is irreducible, this will imply that range of T, you cannot reduce this further, range of T is either the whole vector space V1 or simply the 0 vector space 0. It does not have any invariants, proper invariant subspaces. Likewise, if you look at the null space of T, what does it mean? That means the set of all x for which x in V1, for which Tx is equal to 0. Range of T is V2 because range of T is a subspace of V2. Okay, this will imply that range of T is either V2 or the whole or the 0 subspace. So T maps V1 to V2, T V1 is contained in V2 and this is called the range of T. So if you look at the null space of T is a subspace of V1, and if Tx equal to 0, that means if x belongs to null space of T, then it implies that Tx is equal to 0. That will imply that pi 1G acting on Tx equal to 0, but pi 1G is T pi 2G. So this will imply that T acting on pi 2G x is equal to 0, which will imply that pi 2G x belongs to null space of T. That means the null space of T is left invariant by pi 2, but since pi 2 is again irreducible, it will imply that null space of T is either the whole of V2 or 0. Is the whole of V1 or 0. Since null space of T is invariant under pi 2G under pi 2, so it will imply that null space of T is either V1 or the 0 subspace. So we have two conclusions when you use the fact that pi 1 and pi 2 are two irreducible representations. Either range of T is V2 or 0 and null space of T is V1 or 0. So if range space of T is V2 and null space of T is V1, and null space of T is 0, then it will imply that T is a bijective transformation, that is, it is 1 to 1 and on to. So the case when null space of T is 0 and range space of T is V2 implies that T is 1 to 1, which 1 to 1 on to, which implies that T is a surjection, which will imply that pi 1 and pi 2 are equivalent, but you are not assuming that. So this will imply that pi 1G is isomorphic to pi 2G, they are equivalent representations. That is, you can write pi 2G as T inverse pi 1G T. Okay, but T inverse exists and it is a 1 to 1 on to transformation. That means pi 1 and pi 2 are equivalent representations. On the other hand, if range of T is simply 0 here, then T is the 0 operator and we have nothing to do. We have proved the claim that T is 0. On the other hand, okay, if range of T is V2 and null space of T is V1, if null space of T is V1, then again T is the 0 operator because T annihilates the whole of V1. So So we have a, so this is called Schur's lemma. It says that if T intertwines pi 1 g and pi 2 g, that means T pi 1 g is equal to pi 2 g T for every g contained in G, and pi 1 and pi 2 are not equivalent, then it will imply that T is 0. You cannot have a non-zero intertwining operator. On the other hand, if pi g is a irreducible subspace and T intertwines pi g with itself, then T will be a scalar multiple of the identity. This is the second Schur's lemma. This is very important, because if you assume the vector space to be complex, then T will have at least one eigenvalue, let us say C. So T minus Cx is equal to 0. It will have at least one eigenvector x not equal to 0, and for some complex number C. Now you see, T is a mapping from V to V itself, and pi g maps V to V. Now if you see, the null space of T minus C is invariant under T. Why? Null space of T minus C is because if T minus Cx is equal to 0, it will imply that pi g acting on T minus Cx, that is also 0. But if, since pi g commutes with T minus C according to this, but since pi g commutes with T, pi g also commutes with a scalar multiple of the identity. So pi g commutes with T minus C. So that will imply that T minus C pi g is 0 for every g contained in G, which will imply that pi gx is also in null space of T minus C. So what we have got is that x contained in null space of T minus C implies that pi gx is also contained in null space of T minus C, which means the null space of T minus C is invariant under pi g. So you can write it as pi g acting on null space T minus C is contained in null space of T minus C. But pi g is an irreducible representation. So T minus C, null space of T minus C is either 0 or the whole of V, but null space of T minus C is not 0 because you are assuming that C is an eigenvalue of T. So it has at least one non-zero eigenvector. So this is ruled out, this possibility. That means null space of T is the whole of V, which is same as saying that T minus C acts on x to give 0 for all x belonging to V, which is same as saying Tx is equal to Cx for every x belonging to V, where C is an eigenvalue of T. This is same as saying T is a scalar multiple of the identity on V. This is the second Schur's lemma. Using these two Schur's lemma, you can prove the Schur orthogonality relations, that any two irreducible representations, any two inequivalent irreducible representations have orthogonal matrix elements. Of course, you are assuming the representations to be unitary here. You can always assume it to be unitary because it is a compact group, and as we saw that any inner product on the vector space can be replaced by another inner product which is invariant under the group action, or under the group representation of the compact group, which is the same as saying that under the new inner product the representation becomes a unitary representation. So to prove the orthogonality relation of Schur, you simply use the fact you take pi g, let pi 1 g and pi 2 g be two irreducible representations, and let T be any matrix which maps T2 to T1. So pi 1 g, you consider this pi 1 g, pi 2 g, let us say pi 2 g inverse, which is same as pi 2 g star dg. If you consider this matrix and you call this as P, then if you take pi 1 h acting on P, what do you get? You get pi 1 h g T pi 2 g inverse dg, which is equal to integral pi 1 of, I replace h g by g, so this becomes this becomes pi 2. Now g inverse is replaced by h inverse g, so h inverse g inverse, then dg, because it is a Haar measure which is invariant under shifts by the group, which is same as saying that pi 1 h p is equal to integral pi 1 g t, and here you can write this as h inverse g whole inverse is g inverse h, so it is pi 2 g inverse dg multiplied by pi 2 of h for all h belonging to G, which is equal to P times pi 2 h for all h belonging to G. That means P intertwines pi 1 and pi 2, but if pi 1 and pi 2 are inequivalent, that will imply that P is 0 by Schur's lemma. So if pi 1 is not equivalent to pi 2, is not equivalent to pi 2, right, then that will imply that P is 0, which is same, and since T is arbitrary, that will imply that the matrix elements of pi 1 are orthogonal to the matrix elements of pi 2. You are taking a basis, an orthonormal basis, so that pi 1 G becomes a unitary matrix related to that basis. This is the same as saying that if pi 1 and pi 2, if pi 1 and pi 2 are inequivalent irreducible unitary representations, then pi 1 G A B pi 2 G C D bar d G over G, this is 0. What happens in the case when pi you choose pi to be the same, that means pi 1 and pi 2 to be the same, then you consider the matrix P to be pi G multiplied by T multiplied by pi G inverse dG over G. You consider this and use the same idea to show that, use the same idea, namely the homomorphism property of pi as well as the invariance of the Haar measure under shifts, group shifts. So pi 1 HP is equal to P times pi H for all H belonging to G. And since pi is a unitary, pi is an irreducible representation, by the Schur's lemma this will imply that P is a scalar multiple of the identity. So this is same as saying this is a scalar multiple of the identity C times I. What does this mean? By you can just see very easily that if you write this in matrix notation, this will give you what is the value of the C. Take the trace on both sides. Suppose pi acts in C d pi. Pi acts in C d. That is the d dimensional. It is a d cross d matrix. So if I take the trace on both sides, what do I get? Trace of this will come here, and pi G inverse pi G is identity, and the integral and Haar measure is normalized on G on dG. That means integral dG over G is 1 because it is a normalized Haar measure. So trace of T dG, which is trace of T itself, and that will be equal to trace of P, which is C into D, which is same as saying that I can write this as D times trace of, I can write this, I can replace this constant by trace of T divided by D. Since T is an arbitrary matrix, so what I have shown is that if pi is an irreducible representation, then pi G T, pi G inverse or pi G inverse dG over G is equal to trace of T divided by D. And since T is arbitrary, from this you will immediately deduce that pi G A B into pi G C D bar dG over G is equal to delta A C delta B D divided by D. This is called the Schur's orthogonality relations. So any two, the matrix elements of any two inequivalent irreducible representations of a compact group, they are orthogonal to each other, and within, if you take any fixed irreducible representation of the compact group, its matrix elements are also orthogonal to each other with the coefficient given by this, which is same as saying that root D pi A B G, these elements are all orthonormal over the group. So this is an orthonormal. So if you combine this with the completeness proved by Peter and Weil, Peter Weil proved that the set of all inequivalent irreducible representations of a compact group, they form an orthonormal basis. Orthogonality is proved by this, and completeness is proved by using an argument based on compact operators on a Hilbert space. That is, you take a kernel and you take a G invariant kernel and look at its on the compact group, and you look at its spectral decomposition. So it can be its spectral decomposition, you know the spectral decomposition of a compact operator on a Hilbert space. It has got a finite, a countably infinite number of eigenvalues in general, at most countably infinite, and it has got a discrete spectral resolution of the identity, and the non-zero eigenvalues appear with finite multiplicity, and the zero eigenvalues can have an infinite multiplicity. So in other words, if you consider, say, a kernel like this, K of G inverse H, and you consider G and H varying over G, and you consider the operator which takes K G inverse H into Fh dH, this is equal to Kg acting on G, K acting on F evaluated at G. You define this operator on the, this will be a compact operator because G is a compact group, and by looking at the spectral resolution you can prove very easily the completeness theorem, namely that in fact by using the spectral resolution of this compact operator you can show that the different eigen subspaces, that is if you write the entire Hilbert space L2Gs, if you write the entire Hilbert space L2G as simply range of the different projections P alpha, range of P alpha, alpha equals 1 to infinity, where P alphas form a resolution of the identity summation P alpha, alpha equals 1 to infinity, and whenever it is a non-zero eigenvalue it has got a that is P alpha, trace of P alpha is finite, that means dimension of range of P alpha is less than infinity if lambda alpha is greater than is non-zero eigenvalues of the compact operator K. So K acting on P alpha is equal to lambda alpha P alpha is a spectral resolution of the identity, and using the and considering the range space of P alpha you show that P alpha is invariant under K, and so the P alpha is also invariant under left shifts, under left shift, that is if F belongs to P alpha, F belongs to range of P alpha, then F of G inverse will also belong to range of P alpha. By using the fact that F is an eigenfunction of a kernel, of a G invariant kernel, by using the fact that F is an eigenfunction of a G invariant kernel you get this. So you can use this to show that, to prove the completeness theorem, namely you are using the spectral theorem for compact operators in a Hilbert space to prove the completeness of the matrix elements of inequivalent irreducible representations on the compact group. So you can write any element F as F contained in L2G, that can be written as F of G is equal to summation d pi into pi comma F. Sorry, you should do it this way. You can write it as d pi into F comma pi alpha beta into pi alpha beta G, summed over alpha and beta and summed over all pi varying over all the irreducible representations. You get this representation. So now coming back to our problem, image processing problem, you had a problem in which you had the rotated and noise blurred image can be written as F1 of so G1 is equal to F of G inverse G1 plus W G1. So if I take the group theoretic Fourier transform with respect to G on both sides, that means I compute F2 of G1 multiplied by pi G star, I can choose just an irreducible representation instead of an arbitrary representation, and I denote this as F2 cap of pi. It is a matrix of size d pi cross d pi, where d pi is the dimension of pi, dimension of the vector space on which pi acts. So it is enough to choose irreducible representations, because as we saw in the Peter-Weil theorem that any representation can be written as the direct sum of irreducibles, and so you choose this. If you apply the group theoretic Fourier transform to this side, what do you get? F1 G inverse G1 multiplied by pi G1 star dg, right? What will this give you? By the, it will give F1 of, you call G inverse G1 as a new G1, then this becomes pi of G G1 star dg1. So this is same as integral F1 of G1 into pi G1 star G1 dg1 multiplied by pi G star. So pi G1 pi G1 star is pi G1 star pi G star, so pi G star. Okay, so in other words you get that F2 cap of pi is equal to F1 cap of pi multiplied by pi G star plus W cap of pi. You can simplify this further by noting the fact that how did you define F2 G1? It actually corresponded to F2 of G1 x0, where x0 is a fixed point. So in other words, F2 of G1h will be equal to F2 of G, provided h of x0 is x0. That means if h leaves, if you consider if you look at the subgroup of all elements H in G which fix the point x0, that means the isotropic group h0 is equal to x0, then you have the relation that this is a group of course. So, you will have the relation that f2 of gh will be f2 of g for every g belonging to g and h belonging to h. Likewise for f1, so you can write the relation as f2 of gh is equal to f1 of f2 of g1h, you are rotating it by g, so it is g inverse g1h plus w of g1h for all h belonging to h. So, if you take the Fourier transform on both sides, what do you get? With respect to, first you take the Fourier transform with respect to g1 on this side, then what do you get? You get, you are multiplying it by, you are taking f1 gh, h varies over the subgroup, it is called the little group or the stabilizer group or the isotropy group. So, f2 of gh multiplied by pi g star dg over g is equal to integral f2 of g, say g1 dg1, f2 of g1 into pi of g1 star is nothing but g1 h inverse star dg1. So, that will come outside here, it will become pi h, pi of h because it is a unitary representation into f2 cap of pi, right. Pi h will come on this side when you use the homomorphism property of pi, namely pi g h inverse can be written as pi g1 into pi h inverse. So, if you take the star, pi h inverse whole star into pi g1 star, and pi h inverse whole star is pi of h because it is a unitary representation. So, what you get here by taking the group theoretic Fourier transform is that you get pi of h acting on f2 hat of pi is equal to pi of h acting on f1 cap of pi into pi g star plus pi of h multiplied by w pi. Now, if I integrate over the subgroup, if I integrate with respect to h over the subgroup, I get pi 1 pi h dh with respect to the Haar measure on the subgroup. This is nothing but ph. Ph is the orthogonal projection of CD onto the space of all vectors, x, for which pi hx is equal to x for every h belonging to h. That means the set of all vectors which are stabilized by the group, by the subgroup h with respect to the representation pi. So, if I integrate both sides with respect to h, what I get is that f2 cap of pi multiplied by ph is equal to ph into f1 cap of pi into pi g star plus w cap pi plus ph into w cap of pi. And we have seen that this equation is equivalent to the original equation. This is completely equivalent to the original equation. f2 cap of pi is equal to f1 cap of pi into pi g star plus w cap of pi. This is equivalent to this because of the fact that the f satisfies the relation fg1h is equal to f1g and f2gh is also f2g, and also w of gh is equal to wg for all h varying over h. That is because of the fact that you derived these functions on the group by considering a function on the manifold and then taking a fixed point and looking at this and using the fact that g acts transitively on the manifold. So, this function on the group is completely equivalent to this function on the manifold, and because of this property this equation is completely equivalent to this equation, but this is a reduced set of equations because you are projecting onto pH. So, you can write this in terms of and you can express this as a system of linear equations in terms of orthonormal basis. What is important is that you get an equation in which pi g star comes outside. So, in practice estimating g amounts to estimating pi g star here using a simple linear least squares problem, right. So, in other words you have pH f2 cap of pi minus pH f1 cap of pi into pi g star. Take the norm square of this and you consider different representations. Say you consider different representations, or you take different pairs of images f2k and f1k norm square, and you sum over k, and instead of minimizing with respect to g, you minimize with respect to pi g star. So minimize with respect to pi g star. This is a linear least square problem with respect to pi g, because it is all a linear matrix equation, and you get the solution for pi g very easily. How do we apply all these circle of ideas to our electromagnetic problems? Okay, how? I have some more time, no? I have some more time. So let us try to apply this to an electromagnetic problem. How to apply this to the EM problem? So you have an electromagnetic field described by Maxwell's equations. F mu nu, the rotated field is given by f g inverse x, and you are adding to that noise x, and you get f mu nu tilde x. So what happens is you have two images. The first image is f mu nu 1, or equivalently in terms of potentials it is a mu 1. The second image field is f mu nu 2, or in terms of images it is a mu 2, and you have that relation that a mu 2 is equal to a mu 1 g inverse x. Of course, since this is a vector field, g will also act on this vector field when you rotate it. So actually you should, what you should do to be correct, what you should say is that you take the 3 vector potential, magnetic vector potential, and you take a of g inverse of x is nothing but a of g inverse x, and then multiplied by g here. G is a rotation. So this is the new vector, this is a rotated vector field which I call a tilde of x. I have to estimate x from this, and a is known to satisfy the Maxwell equations. In other words, you have two, of course this is a tilde x, it is gets rotated and noise is also added to it. So a satisfies, I am given this is a tilde 2 of x. What is a tilde 1 of x? A tilde 1 of x, no, the original image is a1. Okay, let us look at this. Let us look at it this way. You have an original field which is a1. You rotate it and add noise to it. I get a2. Okay, I get a2 of x, and a1 satisfies Maxwell's equations. A2 also satisfies Maxwell's equations. Okay, so what I do is I write down the Maxwell equations for a1 and a2. a2 satisfies Maxwell's equations with a rotated source. This will satisfy Maxwell's equations with an unrotated source. So you have the fact that del square of a1 of x minus 1 by c square dou square a1x by dou t square, that is equal to minus mu 0 j1x, where j1 is the original source, and you have del square a2x minus 1 by c square dou square a2x by dou t square is equal to minus mu 0 j2x, that is the rotated source, and you have of course noise also, plus w2x plus w1x plus w1x. So I can write this equation as a system of first order differential equations in time. So I can replace this by, you put a minus here, you put a plus here, remove the minus here, you remove the minus here, put a plus here, put a minus here. Let us say you are taking the speed of light to be 1 to start with. So I can write it as dou a1 by dou t is equal to some v1, and dou v1 by dou t is equal to dou a square 1 square by dou t square. So that is del square a1 plus mu 0 j1 plus w1x. So this is a system of first order differential equations for the state variables a1 and v1. The state variables cover the entire space, contain the entire 3-dimensional space or the space within a cavity. That means if I discretize the spatial pixels, I get a state variable system of state variable equations of the form d by dt of a1 discretized and v1 is some linear operator in this acting in the spatial variables acting on a1 v1 plus noise w1. Likewise I get for the second system. So then I take noisy measurements on these on the electromagnetic field at different points. The electromagnetic field is given by a linear operator acting on A1 and V1. For example, electric field is minus del phi 1 minus del A by del T. For example, if you take in the Coulomb base, suppose you take that the scalar potential is 0, then the electric field is given by minus dou A1 by dou T, which is equal to minus of V1, and B1 will be given by del cross A1, which is some linear operator acting on A1, which after discretization using spatial pixels becomes a matrix acting on A1. So the measurement process of the electromagnetic field involves taking a discrete set of spatial pixels and measuring the electromagnetic field with noise at these pixels. So the measured electromagnetic field at these pixels can be written as some linear operator, linear function of this vector plus noise, say epsilon 1, and I use the extended Kalman filter. I use the extended Kalman filter to estimate A1 and V1 from these noisy observations at discrete set of pixels of the electromagnetic field. So I use the Maxwell equations form the state variable system. The measurement model is a set of discrete measurements at a finite discrete set of spatial pixels with noise, and from that I used extended Kalman filter to estimate A1 and V1 at all points in space recursively. So once I know A1, I can do the same thing for A2 for the rotated electromagnetic field. So you have A1 is A1 at all points TR for all R belonging to the box B is known. You get an estimate of this from the measurements Z1 T using the extended Kalman filter by taking noisy measurements of the electromagnetic field at a discrete set of spatial pixels. Note that Z1 is I get of course estimates of both A1 cap and V1 also. V1 is dou A1 by dou T. Using this I get this, and similarly I do for A2 cap. A2 cap I do the same thing. So but A2 is, so I know A2 at all points. The idea is that by taking measurements at a discrete set of spatial points I am able to estimate the electromagnetic field at all the spatial points by using the a priori information that these potentials, electromagnetic potentials, satisfy the state variable systems, namely the Maxwell equations, right. Similarly I get A2 TR, and then I use the fact that the A2 TR must be related to A1 TR by a rotation. Okay, so A1 hat of T G inverse R plus a noise, some noise field, and then I apply the theory of group representations or group theoretic Fourier transform to estimate G. Here G is acting on this vector, so it is a representation, right. So what I do is, if you want to do it fast, what you do is you expand it in terms of spherical harmonics. That means you take a sphere of a fixed radius and expand A1 TR on this sphere in terms of the spherical harmonics, which is the same as using the irreducible representation theory for the rotation group. So you simply write down A1 cap of TR, A1 cap of T, let us say on the surface of a sphere of a given radius, you write it as summation A1 cap of T Lm into Y Lm of R cap, where these are the spherical harmonics, and then see how G acts on of course A1 hat is a vector, so when G acts on this I will get a representation. This is like this. You see, you are having a model F2 of x is equal to F1 of x, F1 of G inverse x plus Wx, where x belongs to the x falls on the unit sphere S2. So instead of taking group theoretic transform, you can approach the problem in the same way, because by noting the fact that the spherical harmonics, they form a substratum, they form for mod m less than or equal to L, they define a 2L dimensional subspace, 2L plus 1 dimensional subspace, such that the rotation which are invariant under the rotation group. So if I call the span of this as VL or as HL, then L2 S2 can be written as the direct sum of HL, L greater than 0, L greater than 1, L greater than 0. It is a 2L plus 1 dimensional subspace, and each HL is invariant under rotations. That means that if you take YLM of G inverse x, okay, that will be nothing but the corresponding representation matrix pi LG, then m prime m multiplied by YL m prime of x summed over m prime. So it is same as taking the group theoretic Fourier transform by using the fact that this subspace is invariant under rotations under because YLM, you see how do you construct YLM? YLMs are the eigenfunctions of L square and LZ. They are the eigenfunctions of L square and LZ as we learn in quantum mechanics. YLM R cap, this is L into L plus 1 into YLM of R cap, and LZ of YLM, LZ of YLM at R cap is m times YLM at R cap, and L square commutes with R, L square commutes with the rotations. That means L square is the angular part of the Laplacian, L square commutes with rotations. That means L square acting on YLM at R inverse R, where R is any rotation, is same as L square acting on YLM at R inverse R, where R is any rotation. So using the fact that it commutes with rotations, it is easily seen that this is an invariant subspace under rotations. HL is invariant under rotations, and you also prove that it is irreducible by the fact that by using the ladder operators in quantum mechanics. That means if you take any you cannot have a proper subspace of this which is invariant under all rotations. You can prove that by using the ladder operators to calculate Lx and Ly in terms of L plus, which is Lx plus ILy, and L minus, which is Ly, Lx minus ILy. Using the commutation relations between Lx and Ly, you get that, and you can show that L plus acting on YLM will be proportional to YL m plus 1, and L minus acting on YLM will be proportional to YL m minus 1. So you cannot have an invariant subspace of this, because if you start with any YLM, you will cover all the L's by successively applying the ladder operators. So what you have is the following picture. You have A at TR, the original field which you estimated using the extended Kalman filter, and you take a rotation G acting on this vector field G inverse R, and you expand G in terms of, you expand this in terms of, let us say it is on the surface of the unit sphere. You expand this in terms of the spherical harmonics and use the fact that G also, G is also, the map G to G is also a representation of the rotation group of dimension 3. So this becomes a tensor product of two representations acting on a function. G acts on the spatial variables, on the components of A, whereas G inverse here acts on the spatial variables. So I write this as G times summation a vector ALM of T into YLM of R cap of G inverse R cap. Then this will be nothing but G acting on summation G acting on ALM, this vector at time t, multiplied by pi L G m prime m into YL m prime of R, and G acting on ALM is again G acting on ALM, I can write it as in terms of the spherical harmonics. So the idea is that in the end you get everything, the whole equation in terms of spherical harmonics alone. You see, suppose you take F2 of, you did not have any spin variable, any external, any vector variable, you had just a scalar variable, then you have F2 of x is F1 of G inverse x plus Wx. So if you expand in terms of spherical harmonics, what do you get? You get F2 Lm YLM of x is equal to summed over L and M. This is summation F1 Lm then YLM of G inverse x plus summation WLM YLM x. Now you write this as F1 of Lm. So this is invariant under rotation. So it is the representation pi L evaluated at G into m prime m YL m prime of x plus the WLM W term. So you can also write this as, if I define a vector, a feature vector as FLM as m varies over minus L to plus L, if I denote this by F1L, this vector, then this is nothing but, this equation is nothing but the vector F2L, feature vector F2L is simply pi LG acting on F1 of L plus WL for different L's, L equal to 0, 1, 2, 3, etc. This is same as applying taking the group theoretic Fourier transform on the rotation group, because the YLM span, as M varies over minus L to L, they span the substratum of an irreducible representation of dimension 2L plus 1. So again I can use the least squares method to estimate G. That means you take mod of norm of F2L minus pi G F1L square summed over all L and minimize this with respect to G. First you minimize with respect to pi G, this matrix, using a simple least squares, linear least squares algorithm. Now so you get the value of G, and of course you can carry this minimization recursively. That means if you have a guess value G0 and they perturb this to e power t times delta x, d times delta x, well delta x is an element of the Lie algebra of SO3. Delta x can be written as delta x1 into L1 plus delta x2 into L2 plus delta x3 into L3, or more precisely IL1, IL2, IL3, where L1, L2, L3 are the angular momentum operators. Then I expand this up to quadratic orders in delta x1, delta x2, delta x3. I get a quadratic form. If I minimize with respect to delta x1, delta x2, delta x3, I get a set of linear equations for the delta xj's, and that will give you the optimal value of the group element. When you have a vector, when F2 and F1 are vector fields, like in the case of the electromagnetic field, you have F2 of G inverse x into G, sorry, F1 you have this F2 of x is nothing but G times F1 of G inverse x plus noise Wx. In this case you can do the same thing. This is nothing but a representation acting on this is a representation of the group G is equal to SO3 acting on vector valued functions of space, So again I can expand this in terms of spherical harmonics, this F1 in terms of vector spherical harmonics, and convert it into a linear equation of the same form with pi G appearing outside, and then you can carry out the minimization. And you can do a performance analysis also. In the presence of noise, you are estimating delta G using an iterative process by starting with a guess estimate G0 and taking small perturbations using the Lie algebra of SO3, and then calculating the delta xi's by minimizing a quadratic form resulting in a set of linear equations, and you can continue the procedure. You can do this also to fluid dynamics and general relativistic problems. In the case of general relativity, you have a metric tensor G mu nu of TR. You rotate the system, then the metric tensor gets perturbed by T G inverse R, or let us call it as R instead of R, instead of using the notation G for an element of SO3, because you may confuse G with the metric tensor. I use R for an element of SO3. So this gets changed to under rotation R, and the metric will also change correspondingly. So it will be R of mu dash mu, R of nu dash nu, then mu dash nu dash. So it becomes a representation of the rotation group acting on the space of metric tensors. You are, of course, you are now here R mu, this can be in general a Lorentz transformation, right? It acts on 4 spatial indices. So if R is a Lorentz transformation, I can write it as R mu dash mu, R nu dash nu, G mu dash nu dash into R inverse of x. So R is a Lorentz transformation, and you have to estimate this Lorentz transformation. So the first what you do is you use the fact that the G mu nu satisfy the Einstein field equations. So you have a rotate, you have G mu nu 1, G mu nu satisfies Einstein's field equations, and the rotated G mu nu, I call this as G mu nu 2. The rotated G mu nu, or the transformed G mu nu according to the Lorentz transformation, that also satisfies an Einstein field equations, namely of the form R mu nu minus half R G mu nu is equal to K T mu nu. T mu nu is energy momentum tensor of matter. So this will satisfy this equation for G mu nu 1. Similarly for G mu nu 2, you linearize these equations, you get differential equations for the metric perturbations, and you measure the metric at a discrete set of spatial points or spatio-temporal points by observing the trajectories of particles and using the geodesic equations, or measuring electromagnetic fields perturbed by the gravitational field in accordance to the Einstein-Maxwell equations. So you estimate G mu nu 1, the unperturbed G mu nu 1 at all spatial points by taking measurements of the metric tensor at just a finite discrete set of spatial points and making use of the Einstein field equations and the extended Kalman filter. You estimate G mu nu 1 and estimate G mu 2 in the same way, and then once you know G mu nu 1 and G mu nu 2 approximately, you use this model that G mu nu 2 is obtained by applying a Lorentz transformation to G mu nu 1 and noise added to it. Then you get a similar equation of the form G mu nu 2 at x is equal to R mu dash mu R mu dash nu G mu dash mu nu dash R inverse x plus W mu nu of x, and then apply representation theory by expanding this in by looking at the irreducible representations of the Lorentz group, and you determine the invariant, you express this in terms of matrices, representation matrices. You can construct some of the irreducible representations of the Lorentz group by using the fact that the Lorentz group can be realized as SL2C. So you need the representations of SL2C, and that can be obtained from the representations of, just as you obtain the representations of SO3 using representation of SU2C. You can obtain the representations of the Lorentz group using the representations of SL2C, and these are constructed very easily by simply using Weil's Unitarian trick, that SU2C is a real Lie group whose complexification becomes SL2C, and use the same idea, same circle of ideas for constructing the finite dimensional irreducible representations of SL2C, and you can get the infinite dimensional representations of SL2C by namely the principal series by Gelfand's method, or difficulty will come when C is replaced by R, SL2R or SLNR, then you have to use additional representations like the discrete series of Harishchandra and so on, and it becomes a more complex problem. But in general, but for our purposes, it suffices to use the finite dimensional representations of SL2C, because any Lorentz transformation, you see, a Lorentz transformation acts on T, X, Y and Z. Instead you can look at it as an SL2C element G acting on T plus Z, T minus Z, X plus IY, X minus IY, G inverse, G star, or A into this into G star is equal to T dash plus Z dash, X dash plus IY dash, X dash minus IY dash, T dash minus Z dash. So if you take the determinant on both sides, you get determinant G. Since G is a SL2C matrix, its determinant is 1. So determinant of G will be 1, determinant of G star will be 1, and it will follow that this preserves the metric. That means determinant of this matrix is same as determinant of this matrix, which is same as saying T square minus X square minus Y square minus Z square is same as T dash square minus X dash square minus Y dash square minus Z dash square. That means the metric is preserved by this transformation, where G belongs to SL2C, and you also see that this is a Hermitian matrix, right, because the inner thing is a Hermitian matrix. So this can always be put in this form as T dash plus Z dash, X dash plus IY dash, X dash minus IY dash, T dash minus Z dash, where T dash, X dash, Y dash, Z dash will also be real numbers. So it's a valid Lorentz transformation. So by using the fact that SL2C is the double cover of the Lorentz group, that means if G and minus G give the same transformation. So SL2C slash Z2 is the set of proper Lorentz transformations, having a proper orthochronous Lorentz transformation. So you can, from the representation theory of SL2C, you can get the representations of the Lorentz group and apply it to this problem to estimate the Lorentz group transformation by when the metric is rotated. When the metric is rotated, the metric is transformed by a Lorentz transformation and noise is added to it. So, I think this is a good application of group representation theory to the Einstein field equations, wherein we want to estimate the metric of space time by taking measurements of particle trajectories, geodesic particle trajectories or electromagnetic fields at a finite set of spatial points. So, it is a combination of ideas from stochastic filtering theory and group representation theory applied to an important problem in physics, in theoretical physics, namely metric tensor estimation. So, I think I will stop at this point.